So the next cycle to talk about is the diesel cycle. So the diesel cycle is exactly as it sounds. It is the cycle that runs inside a diesel engine, like in a vehicle, and it's slightly different from the Otto cycle. Very slightly, but it is different. So the difference is that instead of an isochoric ignition, the diesel cycle has an isobaric ignition. And that's the only difference. So if you go back and look at the chart or at the PV diagram for the Otto cycle, just the place where you have ignition, where the heat comes in, instead of having that be a vertical line, it becomes a horizontal line. It's the only difference. And so what that results in is that the QH, this is the heat that enters from the hot reservoir, the formula for that changes. We have the efficiency is NCV over TD minus TA. That stays the same, constant volume, that's the isochoric cooling. But then for the ignition, which is the QH part, it's constant pressure. So we have NCP, TC minus TB. And so we can do some simplifying, the n's cancel. CV over CP is just 1 over gamma. So this is just minus 1 over gamma times TD minus TA over TC minus TB. Now this is very, very roughly this, or very close to the same formula as we had for the Otto cycle, at least part of the way for the Otto cycle. Probably not. I mean, I can just draw a sketch. It's just this. But it's identical, except we have ignition here. And then here we would have we would have CBAD. Right. So the point here is that this is identical to the Otto cycle's efficiency formula, except whereas the Otto cycle had just 1 minus this ratio, the diesel cycle has a 1 over gamma in front of that ratio in front. And in particular, because gamma is always positive, because it's always greater than 1, for a given temperature difference between the hot and cold reservoirs, or between the environment, between the hot and cold reservoirs and the cycle itself, the efficiency of a diesel cycle is higher because 1 over gamma is less than 1, which improves the efficiency. So in general, diesel cycles are more efficient than Otto cycles. Also, on top of the efficiency that you gain from this 1 over gamma, the compression ratios that you get, remember that the compression ratio was a factor in the efficiency in the Otto cycle. It's also a factor in the efficiency in the diesel cycle for the same reason. But the point I was making is that the compression ratios are typically, or can typically be higher because the air is compressed without fuel present in a diesel cycle, whereas you don't want to compress the air too quickly when there's fuel present in an Otto cycle, because then you might get spontaneous ignition, which is not good. I think that's called knocking. Now, as a point to make, these are both great engines and we use them in real life, but neither the Otto cycle nor the diesel cycle are reversible. Now, we talked about reversible processes. One type of reversible process is when you just have jumps in your PV diagram. That's certainly an irreversible process, but these are also irreversible. And the reason for this is that the reservoirs are at different temperatures they're at different temps from the temperature within the engine. And the reason this makes it irreversible is that heat only flows from hot to cold. So because the temperatures, because the temperatures inside the engine when heat is flowing from, say, the hot reservoir to the engine, because the temperatures are different, you can't undo that. You can't send the heat from the engine back out into the environment, or vice versa for the cold bit. So that makes it irreversible. Heat flows in one direction only. But what we can do is we can make a reversible cycle in a real engine if we change the process. So the way that we do this is we get rid of, so the trouble here are the isochoric and the isobaric processes, because in those cases the temperature is changing, and so the temperature between the environment and the engine cannot be, there has to be a temperature difference between the environment and the engine. So we have to get rid of the isobaric and or the isochoric process. Those are the parts that make it irreversible. So in this case, we can come up with something called the Carnot cycle, named after presumably a French guy, because usually you pronounce the T at the end of a word, unless they're French. And so what the Carnot cycle lets us do is it allows us to add heat quasi-statically, which allows us to make it reversible. And the way we're able to do this is because, or the reason we're able to do this is because the engine is at a fixed temperature when we need to add the heat. So let me draw the diagram for this. And so the trick here is we are using a different set of processes than isobaric, isochoric, and adiabatic. We've left one out. Come on. There we go. So this is always hard to draw. So we have one like this. All right, I did my best. All right, so we have A, B, C, and D. So from D to A is adiabatic. From B to C is also adiabatic. From A to B is an isotherm. And from B to C, this is also an isotherm. Now, note that they're both curved lines, but as we've gone over in the past, adiabats tend to have sharper or like more steep slopes. And the reason for that is because adiabats in general go as 1 over V to the gamma, where gamma is a positive number, whereas isotherms goes 1 over V, where gamma is a number greater than 1. So this is like, a way to visualize this is like 1 over x squared decreases faster than 1 over x. And that's why the isotherms are less steep than the adiabats. And I've just drawn it more exaggerated. So here we have heat entering the engine during this isotherm and heat exiting the engine during this exiting the engine during this isotherm. And the temperature of this isotherm, it's an isotherm, so it means it has constant temperature. We call it T hot. The temperature of this isotherm, we can call it T cold. So the idea here is that we make it so that the temperature difference between the outside environment and the engine is very, very, very small. So you have very, very, very slow heat flow from the environment to the engine. And because that difference is small, it's very nearly reversible. Obviously, we can't make any reversible processes like exactly reversible in real life. It's actually part of the what we're going to talk about later. But anyway, so just as before, we can compute efficiency. Remember, it's QC or it's 1 minus QC over QH. Absolute value of all of those guys. So E is 1 minus absolute value of QC over QH. And so we know things about what's happening in the process from A to B. So we're going to need to, so our goal is to figure out what QC and QH are in terms of the various state variables of the process. So from A to B, delta U is 0, and that's because it's an isotherm, right? Isotherms always have 0 changes in internal energy. And so that implies that QH is just the absolute value of heat is just equal to the work that, like the output work. And we know the formula for the work done by an isotherm. It's just nR times the temperature inside times the logarithm of the change, or of the ratio of the volumes. Similarly, from C to D, we also have that delta U is equal to 0, which implies that QC, which is equal to the negative of the work in, this is equal to negative nR TC times log of VD over VC. And we can just use a log rule to get rid of the negative sign and flip the fraction. So this is just nRTC over log VC over VD. Just how logs work, right? So what does that tell us about the efficiency? The efficiency is 1 minus TC over TH times log of VC over VD divided by log of VB over VA. The n's and the r's cancel, and then we get the ratio of the logs. However, BC and AD, or sorry, DA, because that's the order of the process, are adiabats. And what does that mean? It means that T times V to the minus gamma, sorry, to the gamma minus 1. Remember this relationship? This is a constant. And we get this relationship from the standard adiabatic relationship, that PV to the gamma equals constant. And then we just substitute, we substitute P for T and another factor of 1 over V using the ideal gas law. We went over this, I think, Monday. But anyway, so T times V to the gamma minus 1 is a constant, which implies that TH times VB to the gamma minus 1 is equal to TC times VC. I think I got, sorry. It's not in my notes, so I have to make sure I get this right. Oh, yeah, that should be a C. V. Okay, so this is T cold, not the temperature at C. It also happens to be the temperature at C, but that's what was throwing me off. So from B to C, we have the temperature at B, which is the TH, times the volume at B to the gamma minus 1 is equal to the temperature at C, which is TC, times the volume at C, which is V, which to the gamma minus 1. That's all. And then we get the same thing for TC VD to the gamma minus 1 is equal to TH VA to the gamma minus 1. Just using the same relationship about adiabats. So again, backing up, I'm just using this relationship that T times V to the gamma minus 1 is a constant along the entirety of the adiabat, and then I'm plugging in what we know about T at those adiabats, it's either TH or TC, and I'm plugging in the values of V at those adiabats as well. So this TC is really like cold temperature, not the temperature at C, although they're the same thing. Right, and so from these two relationships, we get that VB divided by VA, because these are both TH, so we can cancel out the THs, is equal to VC divided by VD, which is nice, because that implies that the logarithm of VC over VD is divided by the logarithm of VB over VA. This is just equal to 1, which, seems surprising, but that's what the math gives us, and that's why the Carnot cycle is particularly nice. So the end result for the Carnot cycle is that E, the efficiency, is 1 minus TC over TH. So what this implies is that a greater difference in temperature between the reservoirs, the hot and the cold reservoirs, implies a greater efficiency. So if your cold reservoir is very, very, very cold and your hot reservoir is very, very, very hot, then what that implies from if you use the Carnot cycle between those two reservoirs to extract energy, you get very, very high efficiencies close to 100%. You can never get to 100% because that would imply that either TC is 0, i.e. at absolute 0, which hopefully, or maybe you guys know is impossible, or you'd have to have THB infinity, which also is impossible. So that's the Carnot cycle. The Carnot cycle is a particularly nice cycle. It's not used in general in a whole lot of industrial environments or in automobiles because it's slow. Because it involves isotherms and very small temperature differences between the environment and the isotherm itself, the heat transfer during that part of the process is very, very, very slow. And so it's just not particularly useful. But if you have enough time in the world, you can convert thermal energy to work at maximum efficiency. Right. So that leads us into another topic kind of easily. It's just not really practically used for anything, just because it's so slow. It's more of a theoretical construct. Like, I mean, in the sense that like you can actually build it, like you could build one, but it's not practical for any means. Like it's a useful. Yeah, I'll leave it at that. It's just not very practical, but such a thing can be built, and there's reason to exist there's reason to believe that such a cycle exists, and this is the evidence. Right. So we're going to move on to another very closely related topic, which is refrigerators. So maybe you guys have guessed, in all of the pictures, all the diagrams that we've drawn so far, engines are always like the Otto cycle, the diesel cycle, the Carnot cycle. These are all engines. The engines always have clockwise PV diagram. So what happens if you reverse those? I mean, like you could, in theory, draw a diagram that has the same processes but reversed. And so schematically, that would look like you have your hot reservoir, you have your cold reservoir, and then instead of taking heat from your hot reservoir, you take heat from your cold reservoir and then add some work to it, and then you take that heat and add it to your hot reservoir, and then you repeat your cycle, but going in the other direction. So here, you take your heat, or you take your cold cycle, or your cold reservoir, you take some heat from it, do some work, and that work allows you to shove that heat, that QC, into the hot reservoir. And so this is what a refrigerator does, right? It takes some input energy in the form of electricity, which is then converted into work, and it uses that work to remove heat from a place that's cold, the inside of your refrigerator, and put it outside, put that heat outside the environment. I.e. it keeps the inside of your refrigerator colder. So in this case, delta U being equal to 0, because it's a complete cycle, implies that the work in has to be equal to the heat out. That's just always generally true. And so that means that the absolute value of the work, Q out, is the difference in, well, let me write this out and then I'll explain. It's the absolute value of the work should be equal to Q hot, the absolute value of Q hot, minus the absolute value of Q cold. So the idea here is that Q out is literally just, well, it's QC leaving the, how do I want to phrase this? You have your cycle. It's going to have some QH coming out. It's going to have some QC coming in. And so the net Q out is QH minus QC, and that's equal to the net work done. And all of that work is input work. Well, not all of it, but regardless. So that tells us how the work is related to the heat that's involved in the process, the heat transfer. Now, the efficiency for a refrigerator is defined differently. The reason it's defined differently is that there's something distinct between work and heat. Heat is a type of energy that is, or it's a type of energy transfer that's random, i.e. there's not a whole lot that you can do with it. And so, in a sense, work naturally will convert to heat, but heat will not naturally convert to work. So, whereas in an engine, our goal is to convert heat to work, we can never get 100% efficiency for the reason I just stated. However, work will very naturally convert to heat. So if we were to calculate efficiency in the same way that we calculate efficiency for an engine, we would get more than 100% efficiencies, which, you know, we kind of try to not call it efficiency at that point, because basically the idea here is, given some amount of input work, how much heat can you remove from your cold environment? That would be a good measurement. Yeah, it is actually because of entropy, and we'll talk about that in a little bit. The question is say you input 5 joules of work into your refrigerator. How much can it cool off? How much heat can it remove from your cold environment given that much input work? And so we call that number, the measure of that, we call it the coefficient of performance. And it's just measured as QC divided by the work, which is QC divided by QH minus QC. And so this can actually be greater than 1, like this coefficient of performance. So that's why we don't really call it efficiency. So we can talk about a relatively simple design of a refrigerator. So let's do that just for some practical applications. So in this design, the reservoirs are as follows. So the cold reservoir is the refrigerated region. That is the region that we are interested in. Keep in mind, the way a refrigerator works is you have like a cold box, and then you have a whole bunch of mechanical stuff, which is the actual engine, or the actual thing doing the process. And then you have the like the outside area. So the thing doing the process is not the cold air, right? That's just a reservoir that we're removing heat from. The hot reservoir is the quote-unquote environment, meaning like the air around your refrigerator. And so the net result from this diagram that I'm about to show you is you put work into the engine, and then heat comes out. That's the net result, meaning that you're going to add in, there's some net work that is entering the engine and some net heat that's coming out, but maybe you add in 8 joules of work, but then 2 joules of work come out in addition. And so even though heat, there may be some heat that actually enters the engine, but overall heat leaves the engine, again, because this is the net effect that we're talking about. So let me go grab the diagram that I wanted to show you. I'm not going to draw it because it's kind of involved, and you know, if I already have it, why waste your time? Right, so the top is a diagram of basically what happens, and the bottom is a PV diagram. So let's just walk through this really quick. So let's start at A. So A is basically here at the top. So you start off with some gas at some temperature T1. We assume we're going to assume that gas is cold. And so that gas runs through the cold region of your refrigerator. This is like the inside of your refrigerator. And so because the gas is colder than your refrigerator, heat transfers from the inside of the refrigerator to the gas, to the gas in the coil. And it does this in a constant volume manner because the volume of the evaporating coil is just fixed. It's just some fixed temperature. Sorry, it's just some fixed volume. So you have heat transferring from your refrigerator, from the cold region, into your gas in a fixed volume process. Then, what happens? So now your gas is up to temperature. It is at the sorry. It is at the temperature of the refrigerator. So it's warmed up a bit. So think from A to B, the temperature increases, as does the pressure. Then you start doing work. Then you actually take energy input from the outside world, like electricity or something, and you push on the gas to do work and compress it. So during that process, that would be an adiabatic process. So no heat goes in or out during that process. So think like a closed syringe that you then push on really fast to make it heat up a lot. So you do a lot of work to increase the temperature of the gas significantly without letting any of that energy escape. So now the gas is really hot and really, really small. Then you feed it through a condenser coil. And the condenser coil is basically, it's just another long pipe, which has and it's long because you want to allow a lot of surface area so you get a lot of conduction. It's just another fixed volume, and now the hot gas runs through that fixed volume, and now the gas is hotter than the surrounding environment, than the air, like than room temperature air. So now that hot gas exchanges heat, again, isochorically, meaning constant volume, with the environment and cools off. And then you put it into another system where it's another well-insulated system where it can then expand adiabatically and give off work. So maybe that work would be reused by some sort of generator to make this thing more efficient, but it cools off without losing any heat. And so, and at that point, it cools off back down to it cools off even more so than the cold environment, because adiabatic processes can decrease temperature pretty dramatically. So you just think one of those cans of compressed air. Those are adiabatic processes, basically. The air is expanding very, very quickly, and so it cools down a lot, and that's why it gets icy and cold. And so it gets very, very cold, and then that cold gas is again fed through into the interior of the refrigerator, and the whole process repeats. And so you have adiabats here, an adiabat here, and then isochoric processes here. And so that's how a simple design of a refrigerator works. Now, this is not how actual real-life refrigerator works. It's just a model. There are some fairly large practical problems with this. First is that you require that the adiabatic what? So the first is that the expansion requires that the temperature get lower than the required low temperature of your refrigerator, which is difficult to do. It means that you need a lot of expansion space to get so it would be a large device. And second, you need your compressor to be very strong to heat up the gas to be hotter than your environment. And so these affect how much, so it's difficult just from an engineering perspective, not from like a physics perspective, to get such large amounts of compression and expansion. But this is how such a refrigerator works. And like designing good refrigerators is it's a real engineering problem. There are refrigerators that use so-called heat pumps, and those can be very, very, very efficient, but they require certain setups. And I actually don't have a very good understanding of how those work, because I haven't looked at them in great detail. Right, but the point is you can reverse any cycle, and it turns an engine, which takes heat as input and outputs work, into a refrigerator, which takes work as input and outputs heat, or removes heat from a system, which is a useful thing to know. Right, so we're going to change gears slightly, and we're going to talk about the second law, or we're going to get to talking about the second law of thermodynamics. So we talked about the 0th law, the first law, now we're on to the second. There are a total of 4. The 0th law usually doesn't count, so then we would say that there are 3 laws of thermodynamics, but there is a 3rd law. We won't get to it. The 3rd law is pretty straightforward. I believe it's just that you can never get to absolute 0, which we kind of already assumed. So before we actually talk about the 2nd law of thermodynamics, we need to understand something that might seem counterintuitive. So there's a question of why don't we see why don't we see objects on the ground suddenly decrease in temperature and jump in the air? So the way to think about this is the temperature of an object is the average velocity of the object relative to the center of mass, right? Sorry, it's the average it's related to the average velocity of the particles in the object relative to the velocity of the center of mass. So like if I throw this pocket knife, the center of mass has some velocity, and it's not like its temperature increases even though the velocity of all of the particles increased, because it's the relative velocity it's the average relative velocity of the particles relative to the center of mass. So the question is why couldn't this pocket knife just suddenly decrease its temperature, i.e. make all of the particles just start moving in the same direction, and then the center of mass velocity would be in that direction. So if all of the particles in this knife, instead of bouncing around randomly doing their thing with some temperature, if all of the particles all of a sudden started moving in a single direction, the temperature would drop significantly, and because all the particles are moving in the same direction, the knife would just jump upwards. So why don't we see that happen? Because that doesn't violate the first law of thermodynamics. Like, the first law of thermodynamics is just that it's basically energy is conserved. So as long as the temperature decreases by an amount that's more than or equal to the amount that the, say, translational kinetic energy of the center of mass would increase, then that's not a violation of the first law of thermodynamics. So why doesn't that happen? It turns out that the reason this doesn't happen is actually related to engines. In a sense, it's the same reason. It's the same reason we can't draw a cycle with heat only coming in and work exiting. Like, there is no cycle that just takes heat and just outputs work, i.e. there's no heat that has to leave the system and there's no work that has to enter the system. No such cycle exists. I.e. you always need some heat leaving. Which is to say that all engines require a cold reservoir. Now, this may seem unrelated, this business about engines, but think about it this way. If I could install a device that did as I described to my little pocket knife, then it would take the heat it would take thermal energy and convert that to heat in this engine, and it could convert that to work, and work would just you could convert that work to just a force on the pocket knife, which would just cause it to jump up. So the fact that this doesn't happen is related to the fact that engines that would do such a thing don't exist. So this statement that we always need some form of heat leaving an engine is a form of the second law. It's not the standard formulation, but it's a form. It's an equivalent definition of the second law. So before we continue, I need to define a few new terms that we haven't actually seen yet. So the first term is an extensive variable. So given a state variable, an extensive variable is a type of state variable. It is a state variable that changes with the size of the system. So examples of such an extensive variable would be the number of particles. If you double the size of your system, i.e. if you take two identical systems and put them next to each other and consider that as a system, the number of particles increases. Similarly, and quite obviously, if you increase the size of your system, the volume increases. If you make your system have more stuff in it, like if you take two identical systems and consider them as one system, you'll have more total internal energy. And similarly, you'll have a larger number of moles. On the other hand, an intensive variable is a state variable that is not extensive, i.e. the state variable remains fixed even if you say doubled everything in your, like, even if you took two identical systems and slapped them together. So examples of this would be pressure and temperature. Like if you take two systems that are identical in every way, they have the same temperature, pressure, volume, all that business, and then you just slap them together and consider it just one system, the pressure is not changing and nor is the temperature. Even though you're doubling the amount of particles, you're doubling the volume, you're doubling the internal energy, and so on. And just from the definition, I don't even need to write this, just using the definitions that I gave you, every state variable is either extensive or not extensive, i.e. it's either intensive or extensive. And so we needed these definitions so that we can kind of try to build the quantities that we need in order to mathematically describe the second law. So to describe the second law mathematically, just like how we had delta U is Q minus W, we need a new state variable, one that we haven't seen yet. We need a state variable that in some sense encodes why, you know, this pocket knife just doesn't suddenly just cool off and jump in the air. So we're going to talk about entropy. So backing up, we know that work arises quasi-statically, meaning you can do work in a quasi-static manner, from a whole bunch of infinitesimal steps. So you just very slightly expand the volume, then you very slightly expand the volume again, and you keep very slightly expanding the volume, and that does very small amounts of work a little bit at a time, and then you add them up and you get a whole bunch of work done from many infinitesimal steps. dW equals P dV. So the idea is you just expand the volume just a little bit, you get a little bit of work done. And you just do that a whole bunch of times and you end up with work. So that's great. It's a great formula that we have that we just derived from the definition of work using force and applied over a distance and then relating volume to distance and so on. But we don't have an equivalent thing for heat, right? Like there isn't a dQ equals something, which we would like to have. So, in fact, such an expression does work. It should look like something the following. dQ equals, well, and I'll explain, quasi-static means internal energy. No, it doesn't mean internal energy is constant. It means that the system is never out of equilibrium. So it should be dQ equals T ds, and I'll explain this in a minute. So S is going to be our unknown new state variable. And the reason why we expect T to be here is that we know that changes in pressure drive work. And so what causes heat to flow? What causes heat to flow are changes in temperature. So in the same way that in dW, we have P times D something, and we know that changes in pressure drive work, for dQ, we should have T times D something because changes in temperature drive heat flow. So we don't know what ds is yet, but we're going to try to work it out. So what is S? Well, so the units, at least, the units of dQ, this is a small amount of heat transferred, is in joules. The units of temperature is in Kelvin. So that implies that the units of S is joules per Kelvin. And so the question is what state variable is this? It's certainly not any of the state variables that we've run into yet. It's not number or number of moles. It's not internal energy, because that would be joules. It's not temperature, because that would be Kelvin. It's not volume, because it would be volume. It's not pressure, because it would be Pascal. So it's something new. So just as a quick aside, temperature and pressure are intensive, and volume is extensive. So we would expect, so using the analogy between work and heat in their formulas, we would expect that S is extensive as well. So we just define a new extensive variable, extensive state variable. We call it S, and we give it the name entropy. That's just, we just define it that way. It is the thing that if you slightly increase the entropy a little bit, then you get a slight or a small amount of heat transfer. It's almost, at least from the construction that we've done, it's defined from this equation, dq equals TdS. So like work, we now have a formula for calculating Q. Q, the heat transfer along a process from A to B, is just T times ds. No, so change of volume. So change in volume is what is kind of the outcome of work. So think of it this way. In mechanics, what actually causes work to be done? Is it the fact that, like if you're pushing on a block, what causes the work to be done? Is it the fact that the block moved? Or was it the force that you're applying to the block that makes the block move that causes the work? So it's the same thing here. So pressure is the equivalent of force here. Volume is the distance traveled. So in this case, it's actually the pressure done. Right, you just need the work for the change in volume. You just need a change in volume for the work to actually be non-existent. But you need some sort of pressure in order for that change in volume to happen. Some sort of pressure difference, rather. Good question. Right, so we can invert these equations, the dW equals PdV and dQ equals TdS, to get changes in state variables. So this is going to seem weird. And what I'm about to do is not rigorous mathematics. So dW equals PdV implies that dV equals dW over P. I'm going to put a slash through that D for good reason. This implies that delta V, which is VB minus VA, is equal to an integral. I'm going to put a slash through the integral as well. dW over P. Now, here's what I mean by these slashes. So typically, an integral is just something that you can do mechanically, but in a conceptual sense, an integral just means a sum over a bunch of infinitesimally small things. So dW just means a small amount of work done. What it is not a small change in the value of work for something, because a thing doesn't have work. So this is just a small quantity of work that happens along the process. This is all to say, the reason why this is a non-standard integral is you're not looking at how a quantity changes, a state variable changes. You're not adding up all the changes in a state variable. You're adding up an infinite number of small amounts of work done, dividing by the pressure along the way, and that gives you a change in volume. And so similarly, we get dQ is TdS, which implies ds is, I'm going to put a slash in the D there. It's not like, I'm not canceling the D, by the way, it's just a slash to indicate it's not like a standard D. It implies ds is dQ dt. And so this gives us that the change in entropy, which is a state variable, which is SB minus SA, this is that special slashed integral. And I'm going to drop these slashes in a minute. It's just the integral of dQ over T. So you add up small amounts of heat that you're adding. So let's say you have a process. During the first microsecond of the process, you add a small amount of heat. You take however much heat you added during that first microsecond, divide it by the temperature during that microsecond, and then you do that for the next microsecond, and then add that small amount of heat divided by the temperature to your first small amount of heat divided by the temperature, and so on. And you add up all of these chunks of heat divided by temperature along the process. And that sum, that infinite sum, will give you the change in entropy. And it turns out that this formula is very useful. So let's just look at an example, or think about an example. If a gas undergoes an adiabatic expansion, what is delta S? How much does the entropy change by? Well, for an adiabat, they don't have any heat at all. So during any small instance of the adiabatic process, the amount of heat added is 0. I'm just going to drop the slashes now just for... So that implies that the integral of dq over t is just the integral of 0, which is just 0. Well, yeah. And so in this sense, it's not a... yeah, and this is from a to b. It's a definite integral, right? And so that means that is what the change in entropy is. So another definition of a new term, an isentropic process, is a process where the entropy doesn't change. And this is equivalent to an adiabatic process. So you may have thought, okay, well, we have isochoric, isobaric, isothermal. Why didn't we have an iso something for adiabatic processes? And the only reason is because the thing it holds constant we hadn't learned about yet. The thing it holds constant is entropy. And so, so what we find then is that so now we can start, instead of calling adiabatic processes adiabatic, we can call them isentropic. Oh, we're making really good time. This is surprising. Like, we're going to finish early, even though today's lecture was supposed to be short. Huh, okay. So far we've given formulas, or like in the past we've given formulas for like pressure in terms of temperature, number of particles, and volume. This is PD equals nRT, right? There is a state, there were state functions for various state variables, like U is NCV times T, P equals nRT divided by V, and so on. So we can do the same thing for an ideal gas. We can derive a formula for this. It's complicated, but so without the details, I'm just going to give you the formula. And like I said, it's complicated. So it's a function of the number of particles, the internal energy, and the volume. And you could have written internal energy in terms of pressure. We have a formula for that. You could have written capital N in terms of little n. But the formula here is N times Kb times the logarithm of this whole thing. So V divided by N times U divided by N to the 1 over gamma minus 1. It's the formula for the entropy. It's just a number. Well, it's a number with units. Kb has the units of entropy, so it's correct. It's just a thing that you got to compute. Right. So you can actually do a lot with this formula. In general, like it's a thing that you can do. But i.e., like you can calculate entropies for given, like that is the entropy of the system, and then you can calculate changes in entropy and so on. But we're not going to spend a whole lot of time using this formula because this is the last lecture. Right. But what we can do is we can compute the entropy change for special processes. So we've learned about all of these processes: isobaric, isochoric, isothermal, and now isentropic. So what is the entropy change for those processes? So for an isochoric process, well, we just compute delta S is an integral from A to B of dq over dt over t. Now we want to figure out how much heat is added for a given small change in temperature. Like we want to change variables from dq to dt. But fortunately, for isochoric processes, we know what the formula is. We know that if you add a small amount of heat and the process is isochoric, we know that the temperature changes by N times Cv times dt. So this is N Cv dt divided by T. And now this is just an integral that you can do. And so we can compute this. This is N times Cv times the log of Tv over Ta. Similarly, we can do it for an isobaric process using the exact same steps, that dq is just ncp dt. So we get ncp times the log of Tb over Ta. For an isothermal process, it's a little bit more complicated, just a little bit, so bear with me. We have delta S, which is again an integral from A to B of dq over T. Now, T in this case, because it's isothermal, this is equal, like we can factor the T out of the integral. So this is equal to the integral from A to B of dq. So that is just the total heat exchanged during the process from A to B, right? You add up all the small amounts of heat added, you get the total heat added. And because it's isothermal, i.e. there's no change in internal energy, we get that this is equal to the work done during the process as well. And we know a formula for the work done. It's nR times the log of VB over VA. It would have been nRT, but we divide by the T because that's part of the term. So that is the entropy change in an isothermal process. But, so all of these can be done quasi-statically. All of these processes can be done quasi-statically. They aren't typically done quasi-statically in real-world engines because they're not done slowly, generally. But this statement, that dq is equal to T ds, is only true for reversible processes. Meaning that's just not a true statement if your process isn't reversible. And I'll get to an example of this in a minute. But first I want to introduce a new thing. So we had PV diagrams, which basically allow you to find the area under the curve, which gives you the work. So we can introduce similar things, TS diagrams, which are the exact same thing, except the area under the curve for a process gives you the heat during the process, not the work. So the example here is you have T, you have S, you have a process that goes from A to B in S space, or in TS space. And so the area under the curve, this is Q. So Q from A to B is equal to an integral from A to B of dq, which is just the integral from, you're integrating over SA to SB of T ds. And so it turns out, God, my nose is so itchy, I hate allergies. It turns out that the Carnot cycle is much nicer looking in TS space. Remember, the Carnot cycle is an isothermal, then an adiabatic, then an isothermal, then an adiabatic. So drawing this process in TS space, remember adiabatics are constant S, isothermal is constant T. So a Carnot cycle just looks like a rectangle where you have A to B to C to D. You have an isotherm here because it's constant temperature, means it's a horizontal line on this plot. An adiabat here from C to D because it's constant entropy. An isotherm from C to D, and then an adiabat from D to A. And so it's a lot nicer. It's actually just a rectangle in this space. So you can see why a TS diagram can be nicer than a PV diagram, depending on the context. Right, so, you know, if you wanted to compute the heat done in a Carnot cycle, then it's significantly easier if you, instead of computing the work first, which is complicated because you have to do a whole bunch of integrals, and then setting the work equal to the heat because the internal energy is 0, you can just find the area inside this block for much the same way that you would do it for work. So now we have to, so I mentioned that this whole dq equals TdS business is only true for reversible processes. So let's talk about why. Let's talk about multiple system setups and see what happens to these quantities. So we're going to consider two systems in thermal contact with each other. And they're in thermal contact with only each other, i.e. they're isolated from everything else, or insulated from everything else. So what we have is we have a system, we have two systems, call it system A and system B, and let's say the temperature in system A is greater than the temperature in system B. We had to pick one of them to have different temperatures, so let's just choose A. So that means that heat, which leaves A, would be equal to the heat that enters B. So for a quasi-static process, i.e. a reversible process, we know that if the total, if Q, which is delta T, so sorry, how do I want to phrase this? For a quasi-static process, we know that delta S1 plus delta S2 has to equal 0 because S is extensive. So the entropy of one system plus the entropy of the other system, if they're once you combine them, should just be the sum of their previous entropies. Just like if you have two different sized systems, two different volume systems, the volume of the total system, once they're combined, should just be the sum of the volumes. So because the entropy, how do I want to phrase this? Because the entropy for the system is a state variable, treating them as the same thing, treating it as just a single state, that there's only internal things happening. There's nothing external happening in this process. It's just reaching equilibrium. So there should be no change in entropy. So if we could get a quasi-static process where this happens, there'd be no net change. The change in entropy of one plus the change in entropy of the other would be 0. But that's not generally what happens. For an irreversible process, let's assume that that this formula still held, that dq is still equal to T times ds. So let's just assume that that's true. So in that case, dq for A would be equal to TA times ds A, dqB would be equal to TB times dsB, which would imply that dSA is equal to dQA over TA, dsB is equal to dQB over TB. And because dQA plus dQB is 0, i.e. the heat leaving is equal to the heat entering, this implies that the absolute value of dSA is less than the absolute value of dSB. Now, why is that? Well, so the dQs on top are the same, but the temperature of system A is higher than the temperature of system B. And so that means that dsB is computed by taking something that's the same as dSA and dividing it by a smaller number, as opposed to dividing it by a larger number. And by the way, dsB without absolute values is greater than 0, dSA without absolute values is less than 0. So I'm just taking absolute values here. So what this implies is that dSA plus dsB is greater than 0. So what we see is that we get that it cannot be the case that S is, so we get a contradiction. And that's because S is extensive. So either X is not extensive, meaning that you can't just add the entropies of the two systems and get the total entropy, or for irreversible processes, this assumption that we made is false. It's just not a true assumption. And it turns out that S is indeed extensive. It's just that dq is not TdS for irreversible processes. So this is just a simple example that if you have two systems that are coming to thermal equilibrium in an irreversible way, which generally does happen because if their temperatures are dramatically different, then it will be an irreversible process, then the entropy that B, or the amount of entropy that B increases by is more than the change in the entropy that, or is more than the amount that A decreases its entropy by. So the overall change in entropy is positive. So the way that we formulate the second law now uses this formulation of entropy. So it's entropy in the second law. The formulation is for any process in a closed system, meaning that it's isolated from its environment, the change in entropy is greater than or equal to 0. And the reason why we say greater than or equal to is we showed that for a quasi-static process, it's just equal, the change in entropy is just equal to 0, just because S is extensive. And we showed that for an irreversible process, the change in entropy has to be greater than 0. So the one way of phrasing the second law of thermodynamics is just that the change in entropy of a closed system over time, when there's any process, either stays the same, i.e. the change in entropy is 0, or it increases with time. So a result from this, a useful application, is we can talk about efficiency in a different way. So remember the efficiency for an engine, which is work over QH. This is 1 minus QC over QH. Can be rewritten as 1 minus TC over TH times delta SC, so the entropy, the change in entropy for the cold reservoir, divided by the change in entropy for the hot reservoir. That's just using this fact that T is equal to, or that Q is equal to TdS. So for irreversible processes, delta SC is greater than delta SH for the same reason that we outlined above. Basically, the heat transfer is the same, but the temperature is lower in the colder one, so it has a larger change in entropy. But now note that this is very similar to the efficiency for a Carnot cycle, except these aren't there in the Carnot cycle. The Carnot cycle, for a Carnot cycle, the efficiency, 1 minus TC over TH, which implies that delta SC over delta SH is equal to 1 for a Carnot cycle. I should put greater than or equal to there. So this is actually a nifty, this is a strange thing that we can do now. We can actually, this is proof, this is like an explicit mathematical proof that the Carnot cycle is the most efficient type of engine. And the reason for that is that delta SC over delta SH has to be greater than or equal to 1. The reason for that is that is just this statement regarding irreversible processes, or statement regarding processes in general. For irreversible processes, it's always greater, but for any process, it's greater than or equal to. So the Carnot cycle is the limiting factor. It is precisely the type of it is precisely a reversible engine, a set of reversible processes, such that the entropy of the system doesn't change. It's a constant entropy. Well, it's not constant entropy. but the increase in entropy of the cold reservoir increases by precisely the same amount as the decrease in entropy of the hot reservoir, which, as is outlined by this inequality, is as good as you can get. So try as much as you want, there are no energies that or engines that you can make that are more efficient in principle than the Carnot cycle. Which perhaps isn't surprising, because you could, in principle, get up to, you could approach 100% efficiency of a Carnot cycle by having a very, very hot, hot reservoir and a very, very cold reservoir. It would just take the age of the universe in order to get it to actually complete one cycle, because it's very slow. Right, and so that takes us through to the end of material for today, for this course. So let me stop recording here.